Building structures atom by atom via electron beam manipulation. This paper was published in Small in 2018. In this paper, we discuss how to manipulate single atoms and show the first demonstration of assembling primitive few atom structures using an electron beam. The ultimate goal of nanotechnology is to develop the ability to create and manipulate structures on an ever smaller scale and put these structures to use for the benefit of mankind. The most well-known example is the miniaturization of computer chips following Moore's law. The success of this endeavor has driven down the cost of computing, making it ubiquitous, cheap, and energy efficient. The ultimate limit is the single atom, and to develop the technologies of the future, today we must grapple with how to manipulate single atoms. Here we use suspended single-layer graphene as our substrate because it allows us to see every atom. When we operate the microscope with an accelerating voltage above the displacement threshold for graphene, we can directly eject carbon atoms from the lattice. When we operate below the displacement threshold for graphene, we can preserve the integrity of the pristine lattice and investigate more subtle changes without continually damaging the specimen. In a previous publication, we described how we can place single atoms into graphene by intentionally damaging the lattice and then sputtering silicon atoms from nearby contamination that subsequently attached to the damaged lattice. We also illustrated how a silicon atom can be intentionally moved through the lattice. Here we start with a similar insertion process to generate many silicon dopants. Again, we illustrate the ability to move silicon atoms step by step through the graphene lattice, in a line, and also in a circle. But if we want to build structures atom by atom, we need to start bringing atoms together. Here we begin with two three-fold coordinated silicon dopants that have been inserted into the graphene. Using the E-beam, we were able to step them toward each other until they were positioned together in the same hexagonal cell. At this point, one of the silicon atoms was unintentionally ejected from the lattice and lost, leaving a single four-fold coordinated silicon atom. Theoretical simulations from first principles reveal an energetic favorability for the agglomeration process, shown here in the decrease in energy as the atoms get closer together. The precise mechanism through which the silicon atom was lost is unknown. However, this too represents an energetically lower state than the harboring of two silicon atoms. If instead we begin with two four-fold coordinated silicon atoms, that is, each silicon atom is sitting in place of two carbon atoms that have been removed from the lattice, we will end up with a different final structure. The hexagonal symmetry of the graphene cannot be maintained because there are two atoms missing. After forming this structure, we observed a spontaneous healing of the lattice. Two carbon atoms are observed here attaching next to the silicon atoms, restoring the hexagonal symmetry. This new structure is now the same as the one we made previously and shortly resulted in the same final outcome, namely loss of one of the silicon atoms and the formation of a single four-fold coordinated silicon atom. In this example, we begin with this structure, but here, instead of forming it ourselves, we just happened upon it already formed. But we observed a different transformation process. Instead of healing, a bond rotation occurs in the middle of acquiring this image. These two atoms rotate by 90 degrees. According to Yang et al. In reference 37, this is a reversible process, although we only observed it rearrange once. After the rotation, a third silicon atom diffused into the field of view and attached temporarily to the rotated atoms. The influence of the electron beam quickly knocked it away again. It returned a few moments later and then replaced one of the carbon atoms involved in the bond rotation, likely due to the added energy of the beam. The result is a silicon trimer that can easily be rotated by positioning the beam next to it, shown in these two panels. If we scan the beam over a larger area, mobilizing the surrounding materials, within a few tens of seconds, we can induce the attachment of a fourth silicon atom at the center. This structure can also be rotated, and the central atom can be removed by parking the beam on it. These demonstrations represent the first steps toward building structures one atom at a time, using a scanning transmission electron microscope as an atomic manipulation platform. Links to the publication as well as the ArXiv version can be found in the comment section below.